In this course, we're mainly dealing with finite populations. Finite population means that in principle, if not in practice, you could enumerate all of its elements. For example, all the households that exist in the UK on a particular day, or every person alive in the UK on a particular night. A complete enumeration of a population is called a census. In reality, a census is likely to be incomplete. How incomplete it is can be a matter of empirical investigation, as can how much the incompleteness matters. A census can be very expensive. The recent census in England and Wales in 2021 is estimated to have cost about £800 million. There is often a trade-off between extent of coverage and quality of what is collected. Sampling from a finite population to improve the quality of the data collected and produce estimates of the population quantities of interest was controversial before the turn of the 20th century. The Norwegian Anders Nikolai Kjær and the Englishman Arthur Bowley were influential in developing the practice. The Pole Jerzy Neyman developed and systematized the statistical theory in the 1930s. Now, some more definitions. Probability sampling. Probability sampling is a sampling method in which every unit in the population has a known and a non-zero probability of being selected. Let me say that again because it's very important. Every unit in the population has a known and non-zero probability of being selected. Probability samples come in different flavours, and I want to mention 4 of these. First of all, simple random sampling, or SRS as it's sometimes known. In simple random sampling, every unit in the population has the same probability of being selected. Secondly, stratified sampling. In stratified sampling, the selection probabilities are set separately and often differently for different groups known as strata in the population. Examples of strata are the two sexes, or different age groups, or people living in different types of housing, or people living in different geographical locations or regions. The third type is cluster sampling. In cluster sampling, the units of interest are not sampled individually, but in groups or clusters. For example, we might sample households and then interview every adult in the household. The household would be a cluster, and then in the second stage, we interview all the adults in that cluster. Finally, multi-stage sampling. In multi-stage sampling, this involves a sequence of steps. Firstly, geographical units, perhaps postcodes, are stratified by population density, index of deprivation, region, and so on. Then, the postcode areas, which are of course clusters, are sampled from the strata, and households, another cluster, are sampled from the selected postcodes, and then finally an adult is randomly sampled from the household. The important point to get here is that all of these methods lead to a probability sample, in the sense that they all give a sample where the probability of selection of the individual elements is always known. Having introduced 4 different types of probability sample, we're now going to ignore 3 of them. For the purposes of this course, we're going to assume simple random sampling. Why are we going to do that? Well, because you have to learn to walk before you can run, because the principles are clearer if we don't get bogged down in detail right from the get-go. Let's get the overall shape of the wood right, and then we can examine all the trees later on. Another reason is, of all the things you need to worry about when you're just getting going, details of sample design, though ultimately they're rather important, they're not the most important thing that you need to concentrate on at this stage. And finally, you can't learn everything at once. A very pragmatic reason is that plain vanilla versions of software will usually assume that a sample has been generated by simple random sampling. Though, of course, software for dealing with more complex sampling designs, such as the ones that we've mentioned, also exist, even in R. Sampling is not synonymous with probability sampling. There are also non-probability ways of sampling. Let's consider 3 of these. Firstly, purposive sampling. In purposive sampling, the investigator uses his or her own expert judgment to select units they consider representative of the population. Unfortunately, conscious or unconscious bias means that this is probably not going to go very well. As people often say, what could possibly go wrong? Secondly, haphazard or convenience sampling. That amounts to selecting whoever happens to be available or self-selects in by volunteering. Examples of this are things like internet polls or the sort of social media poll that one sees from time to time on platforms like Twitter. Finally, quota sampling. In quota sampling, interviewers are required to select a certain number, a quota, of respondents in each of a set of categories: sex, age, social class, so on and so forth. Who exactly is selected is left to the interviewer. All of these non-probability sampling methods share the characteristic that ultimately we don't know the probability that a unit will be selected. It could, and quite often is in fact, 0. This makes the statistical basis for making an inference from the sample to the population, which after all is what we are usually ultimately interested in, at best unclear. You might think it should be a straightforward thing to draw a sample from a population in order to use the information in the sample to make an inference about a characteristic in the population that you're interested in. But in practice, this is not always the case, and this graphic illustrates some of the difficulties. Down here in green, we've got our sample, and in black, we've got what I've called here the target population, the population that ideally we would like to make an inference about. So what's the difficulty? Well, first of all, there may be some practical reasons why the target population, some members of the target population, are not really accessible. There might be, in other words, a difference between the target population and the population that we're actually able to survey, the so-called survey population. I'm trying to indicate that by drawing this dashed line across here, suggesting that this portion of the target population might actually in practice be unavailable to be surveyed. Why might they be unavailable? Well, let's say that our target population is all of the adults in the United Kingdom who are resident in the UK on a particular day. It may be that it's just not practical to actually sample some of these. For example, the prison population might be very difficult to access. People living in long-term institutional care may be difficult to access, and even if you could access them, they may not be able to respond to inquiries about whatever it is that you're interested in. Sometimes as well, interviews with some of the target population or collecting data from some of the target population is simply ruled out by other sorts of practical reasons. In the UK, it's very rare, for example, for face-to-face interviews to be carried out with anyone who lives north of the Caledonian Canal up in Scotland, simply because the expense of sending interviewers right up there to interview the one or two people who might possibly be selected into the sample are disproportionately large. So when we exclude some of the target population, we're really trading on the fact very often that that proportion is so small or so negligible that excluding them, effectively giving them a selection probability of 0 for being drawn into the sample, really won't have a big effect on any inference that we're likely to make. Okay, so we're making a distinction here between our target population, what ideally we would like to make inferences about, and our survey population, what in practice we can probably make inferences about from our sample. But there are other difficulties. In order to sample anyone from the survey population, we actually need to have some kind of list of the elements in the population. In order to select them, we need to know who they are, or at least have some identifying information so that we can select them. In other words, we need a sampling frame. A sampling frame is simply a list of the elements. That's indicated by this red circle here. And you'll see that the red circle is slightly offset from the black circle, indicating that these two don't necessarily completely overlap with each other. Why is that? Well, there may simply be some people in the target population who are not included in the sampling frame. There may be some people, for example, who are missing from an electoral register, or whose household for one reason or another is not recorded in the postcode address file. All of these would be examples of so-called non-coverage. On the other hand, the sampling frame might actually include some people that we don't want in there. For example, in the postcode address file, which is simply a list of postal addresses, and presumably we assume that that's coterminous more or less with households, there may be people in the household who are not adults, for example. There will be children in the household, and if our interest is in the population of adults, clearly the children are out of scope, and we would have to find some way of filtering those out. Okay, so basically what we can do at the end of the day, or all that we can do at the end of the day, is sample from our sampling frame, whatever this is. So let's assume that we've actually got our sample, we've selected our elements, probably by some probability method, or hopefully by some probability method. What could possibly go wrong now? Well, what can possibly go wrong is that some elements in the sample simply refuse to participate. They refuse to give us the information that we're interested in, or we're not able to collect them, perhaps we're never able to contact them. This is usually called non-response. And of course, what we worry about a lot is whether the characteristics of those that don't respond to our inquiries are similar to the characteristics of those that do respond. In an observational study, for example, a social survey, where we sample from a finite population, the target population, in some sense, has a real existence. The relationship between the sample and the population, though complicated in ways that the previous slide illustrated, is reasonably straightforward. What about an experiment, though? In an experiment, we may randomize subjects to an experimental and a control condition, and then measure the outcomes in both. What's the population? The relevant population in this case is clearly conceptual or hypothetical. Whatever the population is, it's certainly not finite. But what exactly is it? We can think of the outcomes we observed for those randomized to the experimental treatment condition as a sample of outcomes from an implicit population. That population is all the possible values of the response variable y subscript e for those who were or might have been exposed to the experimental condition. We can apply a similar logic to those who were or might have been exposed to the control condition, but with the focus now on the response variable y subscript c. Unless we think that everyone in the experimental condition will have exactly the same outcome and everyone in the control condition will have exactly the same outcome, we're obviously dealing with two conceptual population distributions. Let's look at an example. We want to evaluate a new method of teaching statistics. We randomize students to either receive instruction in the new way, the experimental condition, or the old way, the control condition. At the end of the course, we give them all a test. Clearly, the focus of interest is whether the new method is better, worse, or indistinguishable from the old method. Say our two conceptual populations look like those illustrated in the figure on the left-hand side of this slide. The red curve is the distribution of outcomes that would be observed if everyone in the relevant population received the experimental treatment, and the black curve is the distribution of outcomes that would be observed if everyone in the relevant population was in the control condition. If we had 60 students and we randomized 30 to the treatment and 30 to the control, what we've done is we've created a sample of 30 draws from the experimental condition, from this distribution here, the red distribution, and 30 draws, y subscript c, from the black distribution, from the control distribution. We'll want to use that sample information to draw an inference about whether the parent populations, which of course are unknown to us, are different or similar. Let's consider another scenario. We have data for a UK general election on all the constituencies that were contested. We want to explain the share of the vote in each constituency that has gone to the Conservative Party. We've also got information on relevant predictors of that. For example, the class composition of the community, whether the incumbent is from the party, and other relevant things. Now's the question. What here is the population? There's only one observed election, but are we interested in just that? And the answer to that is probably not. What we most likely want to learn about is what might happen in circumstances that were similar in most relevant ways. Now, obviously, some things would be different. Different people might turn up to vote. The election might be on a different Thursday. Those that turned out might change their mind at the polling station. We could regard the actually recorded votes as a sample from the population of electoral outcomes that might have been realised. The experiment and the election example have something in common. In both cases, the population of interest is in some sense hypothetical or conceptual. It's a population of possible realisations of events. The data actually observed can be thought of as a sample from that population. We could take this a little further. Consider Census Day in England and Wales. It was Sunday the 21st of March 2021. But there are fuzzy edges. Is someone who moves out of an address before the end of the day living there? Are we only interested in the more or less finite population of those living there on that precise day? What about Saturday the 20th or Monday the 21st or a day in April? The population is only truly fixed and finite at one small moment and will be ever so slightly different at other times. We could view the finite population at a single moment as a sample from a conceptual population of possible relevant realizations. Such a conceptual population is sometimes referred to as a superpopulation, and it can be used to justify the use of techniques of statistical inference on something that otherwise looks very like a population rather than a sample.